Session is handing over to you, sir.
Thank you, and good afternoon to all of you, all the listeners and viewers. I hope you can see my slide, and also I hope you can listen my voice also. Is okay?
Yes, sir.
Okay. So I'm very happy and glad to note this NIT Delhi is organizing this 5-day FDP program. And being a Saturday, although they started on 25th and it will be going on 29th, I guess. So it is
Yes.
a 5-day program, and all they are utilizing the holidays, I can say, because 25th, 26th, and 27th are holiday. Only the 2 days, 28 and 29 are working day, and maybe it is also vacation period also. It all depends upon the academic curriculum. So this Saturday afternoon, no doubt, I'm in my office and I'll try to focus. The theme, as you know, the theme of this FDP is alternative energy sources in the grid. And my talk is also related to the grid, and we are talking if you are integrating more and more renewable energy sources, what is going to happen? So I thank all the in the beginning itself, because many people will leave once I'll go ahead, because being a Saturday. But thank you, this Srivastav and the Kumawat and other his team. Regularly they are organizing the various events related to electrical and other fields of research. So in this talk, basically, I'll be talking about, you can say, three different colors, because one is the estimation, another is the grid harmonics, and the other part is the renewable energy sources. So my talk will be, if you are connecting the renewable energy sources, what are the grid harmonics they can enter, and then if you are there entering, how you are going to estimate it. So the estimation is a very, very important, because we know many simple algorithms, like most of the
क्या
devices use.
हम्म
Can you ask all the people can mute, and then being a host, you can mute all the people, and then we can talk, because something background sound is coming. Hmm. This is the problem with the, I think, video and virtual mode, because people forget to mute their mics. So once you are speaking, only you can just unmute. Otherwise, you should be muted. It will be always better. And also, you can even stop your videos, because the bandwidth issue, many people will be not able to access the videos and the voice. So it is always better if you are only you are speaking, then you can turn on your mic as well as your video. So anyway, so here I was telling that we are connecting more and more renewable energy sources. They are going to pose many problems. I'll be discussing some of them. And one is the harmonics. So harmonics, if it is a small amount and it is, you can have some device to ground it, not to enter into the grid. So always it's better, because you cannot make the harmonics zero, because nowadays many devices, earlier we were also having devices, but those devices are generating very less amount of harmonic. But due to the power electronics devices, and these renewable energy sources are connected with the power electronics devices, they are very prone, and that's why this topic I am going to discuss. Now you can see that this harmonic estimation, it is one small part of the power quality, because we know the power system design and operations, we are having the 5 concerns, and these concerns are from very beginning when the power system was growing. And and each here topics, normally we are having one course on that. You can see the economic dispatch is the last bullet. It is the, this economy is always we do and study the economic load dispatch. Normally it is sometimes we go for the minimization of capital costs, operating costs, maintenance costs, emission costs, control action costs. Many things we are minimizing, and we see the economy of the system, so that we can reach uh, with the cheaper electricity to our end users. Stability, you all know, because the power system we are having the synchronous operation is needed, because we are having the set frequency of operation, and many devices are basically connected with the frequency operation. So they should have in the synchronous, and they should not even deviate during the disturbance, even though after disturbance. Security is related to operation. We operate our system in much secure that we can maintain the voltage and also the line flow within the limit. Otherwise, the violation will be there. If the violation is there, so grid may fail. So we also go further. It is operation related. Reliability, once you are the planning, once you are designing the system, we design the system in such a way. For example, always you see suppose there is a one connection between the two, even though overhead transmission line, and it is basically connected with underground cable or even the overhead cable. So always you will find that there will be two parallel cables normally we put, because we believe if one cable bursts, there some problems happen, so still we can provide the power. So to make the reliability. Also, the transformer, once we design, it is always, we believe that it should not be loaded more than 80%, because some load is fluctuating, this should not cut fire. But these are the planning issue, but the planning issues are very, very challenging. And nowadays the planning issues are people are not doing, simply we connect and keep on augmenting, and the load is changed. We are going to put another transformer, another line, and so on and so forth. So the reliability is a loss of load probability related issue. And that's it. But power quality, beginning we were always concerned about the frequency and the voltage deviations. And if it is within the range with the continuous supply, we are saying, oh, good, quality of the supply is good. So nowadays, in the quality, due to the power electronics, various things are coming. Now people are saying, forget about those deviations. No doubt they should be there. Along with that, we want the perfect sinusoids. And these sinusoids, basically, if you are having some range of the deviations in the sinusoids, it is acceptable. And then we say, what is the TSD level, total harmonic distortion or individual harmonic distortion. So the quality has basically gone in the different phase, and a lot of issues like it is notching, flickering, transient, sag, swell, all these things are because the harmonics, etc., they are coming into the picture, sometimes short term, sometimes long term. And the quality is going to be one of the bigger concern in the near future, because we are keep on integrating our renewable energy sources. We are keep on putting the power electronics devices for the various, for good reasons. No doubt we are putting the power electronic devices for various good reasons. But at the same time, they create some of the problems and they are affected the most. So the quality is one issue. So my talk is related to the quality of these 5 indices, where one part I'm taking is the harmonics if you are connecting the renewable energy sources. So always we know that's our this power system and how we are going for the smart grid and other things. A lot of things are happening. We are connecting in the more and more renewable energy. So the future power system will having more and more. So that's why you can say every month we are adding almost 1 gigawatt of the solar power on average. Minimum I can tell you. In early, even though years of 19 and 20 beginning, we were adding even more than that. So we are keep on adding the renewable energy sources. We are trying to have nuclear as well as clean coal, and we also augmenting the market, because load follows generation. Means if the generation is more or less, means price will be more and less accordingly. If the more generation, price will be less. Then we have to consume loads. So this is a demand response, and other things are coming in smart meter, communication, IT. All the things are going to club in these, basically our power system, to again make more and more efficient, more and more reachable, more and more giving the customer values. Many, many things we are trying to do. So that's our future power system is now going to have more renewable energy sources. Now coming to the renewable energy sources. Renewable energy sources, you can see that it's a no doubt, it is available in the abundance, it is in nature. Many of the things, renewable energy sources, and they are excellent natural resources, energy resources, you can say. They are the environmental friendly, low operating costs, and so on. Many, many advantages. Not only these two, we can list out the many advantages of the renewable energy sources, but people are say it is a question is environmental friendly. For example, if you're going for a small hydro, if you're going for wind, even the people are saying if you're putting the wind in the sea, even though fishes are deviating and going somewhere else, and the fishes are even though dying. So even though it is highly debatable, but we have to see if you are emitting with the power with the coal fired, and if you are going for wind and solar, how much environmental carbon footprint is reduced, and it is a huge and very drastic. So they are having a lot of advantages of these renewable energy sources. But the major problem with these devices, especially, in our country, we are mainly focused on the solar. Earlier, we were focusing more on the wind. So we were focusing more on wind because the wind is only limited in the certain states and certain area of even the states. You can see it is basically it is coming in the Gujarat area, it is coming in the Maharashtra, it is coming in the Kerala and Tamil Nadu. So some of the part they are having the wind, but like other Europe country, the wind, etc. The people are going the wind farms in the seaside, and inside the sea, maybe 70, 80 kilometers they are going, which we cannot go because our sea is very deep. If one's just going even though 20, 30 meters ahead, it is so deep because construction of the foods and the turbine, etc. is very, very difficult. But no doubt in the future, people are doing the research. If we can have, let's suppose, floating turbines, even though people are doing, if the floating wind turbines can be very commercially available, then we can also use, because we are also surrounded by almost the 3 areas of our country, and we are having huge sea area where we can generate lot of power. But that is again the future, and we don't know whether how much we are reaching. But the only I can say, only on the land, we are having the limited wind. And that's why the government now it is focusing to go for the solar. And you know the solar, we are having approximately 300 days, clear sky days in our country out of 365. So you can see in these, we can trap more and more renewable power. And even though we can use the rooftop, we use the barren lands, we can, even though many ways, even though we are putting on the canals, we are putting on the roads, we are putting in the parking areas, many spaces that we can use for even the multi-purpose. Even the US, the people generated 10 megawatt power in one of the stadium. Just you can say such a huge stadium, if you can also put on huge power can be generated, so that the whole power can be generated and can be utilized inside that stadium itself. And most of the time you can say the stadium is not used for any purpose, and only once matches are there. So there are many places where the solar can be generated. Even though our government is putting at the airports. And even though you can see in Delhi, if you're landing and taking off, you can find the one side, a lot of solar panels are there. So solar, the government, our Indian mission is very drastic, and we are putting more and more solar every time, as I said, and that is basically beauty. So the problem you can see, it is intermittent. Because once you know, if it is a cloudy, you will have less power generation. No doubt it's not related to temperature, even though it is not directly related to sunny time. Even though it is not sunny, still you'll find some generation because it is related to the incandescent, as you know, solar radiance. So that basically required to generate the solar power. But this wind and solar, they are nature dependent and very intermittent, because sometimes very high value, sometimes less value, sometimes zero value. And we cannot control them on its own. Means they are not dispatchable generator. I mean, that you can shut off, no doubt. You can make it zero. You can reduce it what it is the value, but you cannot increase. For example, it is generating a maximum peak, and I want more power. You cannot increase because it depends upon the nature. So they are not perfectly dispatchable generator, because the reduction is possible. You can control and you can say, okay, I don't want to generate. You can even though disconnect also, you can make zero also. So, but it is not a fully controllable. That is one thing. However, other synchronous generators are very well we can control. Very well we are, we are having our governor control. We are having our field control. So we can both voltage and reactive power, voltage and your frequency can be controlled very easily in the synchronous machines, which is not possible here. People are trying to control, no doubt that a lot of people are working that how we can control in such a way that if can increase the inertia of the system. So, and these devices are not having no inertia or less inertia. For example, solar has no inertia, but wind turbine, if you see, it has some some inertia, because it is at 80 feet, basically blades are there and they are rotating. So some mass is there, but at the same time we can control by their pitch angle. So the inertia can be controlled, but it is not sufficient. So those countries where more winds are there, they put the big induction motors with the flywheel connected so that they can control the inertia. Because if your load is very small and where wind percentage is more, this fluctuation will be very high. So suddenly your load is increased, sudden frequency will go and up. So the window of the frequency variation will be very large, and we want to very tight window in our country itself. We want even though the frequency should not be deviating the 50.1 both side plus minus 0.1 or 0.2 maximum we want. So that basically the inertia is one of the. So that's we are going to more and more. Then inertial issue will be another things that can be seen, and people are working on these areas. But at the same time, we can use certain way of the maybe power electronic devices. So to control the power, we can have the storage. For example, suppose there is a night there's more wind, but load is less, you can store it. And a lot of various type of storage. One we know very well, battery. The battery we very well know, but there is some other storage, maybe thermal storage, maybe hydrogen storage, many type of storage that we can work, and then we can interconnect these with the other system so that we can have the very proper and stable operation. So, and for doing all these three things, the power electronics do the job exceptionally well and become an interface between the renewable energy sources and end user. So whenever any renewable energy sources you will see, the power electronics, I can say at this time, it is a must. You see this diagram. Wherever you will see, whether it's a wind, whether you see the PV, whether you are even looking at the smart home where the grid controlled solar systems are here on the rooftop, everywhere you can say the charging, discharging, computers, everywhere the power electronics. So this as a generation side, at the end user side, we are putting more and more power electronics. But no doubt the transmission system is also not is untouched with the power electronics devices. As you know, we are using the fax devices. We are having the SVCs, we are having the thyristor control reactors or thyristor TCSCs. So we are putting on the system. So the transmission is also having the power electronics. Generation is also going to have a power electronics and the end user. So the everywhere the power electronics devices. And these power electronics are the big concern. The major issues and challenges in the renewable energy sources is the interconnections. Now again, we require a very rigid grid code. Right now, the grid code is a draft is available. It's anytime the CRC can approve it. So at what level, suppose you are having a 5 kilowatt power, at which voltage you have to connect? The commercially I want. If the distribution system is there, no doubt you can utilize in your house itself. So, but the interconnection issues at the big farms of solar farms or you can say wind farm. So what will be the voltage level where you can connect and what will be the topology and how they are going to treat in the system if there is any disturbance. So that's why people talk about the LVDRT and even the high voltage, all these things, if the disturbance is there, so that's a right through capability can be also checked. Handling of the load generation mismatch means how to control the frequency and the active power. This is another challenge. If you talk about the PASOCO, which is operating our national grid, they are always worried about the sudden drop or sudden increase in the power demand or sudden decrease in the renewable energy sources. Huge power mismatch is there, and that must be met by our thermal, hydro, nuclear, as well as the gas power stations. So that's we have to maintain with this frequency and active control. And because the renewable energy sources at this moment, we are trying to trap as much as possible, that's why we go for the maximum tracking points. Say whether it's a solar, whether it's a wind, we are trying to trap if it is available and inject into the grid because still we are having the very limited percentage. Another concern about the reactive power control, the voltage control. As you know, the voltage is a local phenomena. It is not that generators are controlling the synchronous generator, the excitation control. Our voltage control is there where the reactive power we can set. We are having various shunt devices like capacitors, LTCs, online tap changers in the transformers, capacitors, thyristors, and even though SVC, they are there, we are controlling. But if you are putting the renewable energy sources, more wind, more solar, then at that time also in the wind, we require some reactive power compensation devices at its terminal. Same time, we are having PV, we can. So what people are thinking, because if you are using the power electronic devices, it is possible that we can control the voltage also with the capacitor connected across this. And that is a reactive power control is also another concern, and people are trying to work on this. But moreover, these renewable devices are designed and rated, especially for the active power, how much they can give. But in the peak hours, no doubt they are giving the maximum power, so the current is flowing into the power electronics devices. But in the off peak, means if there is a peak is not there, so we are having capability. We are having certain margin that current can be increased, reactive current can flow through these thyristors or power electronics devices, and we can control the voltage. Especially in the night, PV is almost idle. So why not we can control the reactive power during the night time with the help of the same device. So all the things people are trying, and they are thinking why not we can utilize. So the frequency, as I said, if there's a sudden jerk, one is the active power control is related to the frequency, another is stability. Because suppose your grid fails, or suddenly there is a sudden disturbance in the system, what will be role of these power electronics devices along with the renewable energy sources? Whether they should be disconnected or whether they should support it, because they are very prone, they are very much affected. So for that, we require the grid control. Another concern is the transmission constraints, because if you're connecting, sometimes you'll find because they are generating maximum power and the grid, that's the distribution system or transmission system, sub-transmission system where they are connected at the low voltage, that's going to be congested. And maybe if we are injecting in the grid, some of the grid lines which is interconnected, maybe they're congested. So who is going for a few hours, maybe only constraints are there, limiting constraint. Other time it is normal because the wind is coming at sub time, solar is coming only in the daytime. So all these things are transmission constraint, then we have to strengthen them. Once you are strengthening, then you have to go for the huge cost on that. If you are going the cost, you have to see whether that power injection is good enough to maintain the cost and recovery of the cost, etc. So that is another concern. Second concern is about the protection and the reliability, because many of these devices, if you're having the DC current and to protect it. So that's what normally we do in HVDC. As you know, we are working for the controller of the converter itself. We don't have the circuit breaker. And now, of course, the ABB and other, they are making the commercial circuit breaker. But normally the philosophy of HVDC lines are basically nothing but they are with voltage control, and they're controlling even the controller of the converter station itself. So the protection in the distribution system, when it was flowing the unidirectional of the power flow, now connecting these renewable energy sources where the current is flowing here and there. So the overcurrent protection may not be very effective, will be used in especially the radial distribution system. So we have to see change the protection system, and then again the cost is going to high, and we have to see which protection system we are going to be using. Reliability is related to design, as I said, because it is sometimes some system is failed, and then the power we are unable to inject. Suppose one time distribution network is down, sometimes you are having renewable power and it is not able to inject in the system. So all the things are basically the concern that is we can do. And another concern is no doubt your power quality issue, which as I said, I'll be discussing this power quality, where the harmonics is only I'm talking. I'm not talking about the flickering. I'm not talking about the notching. I'm not talking about the sag and swells. I'll not talk about the transients, etc. But let us talk about the harmonics. As you all know, there is a harmonics in the two types of harmonics. One is the multiple of fundamental components, and another are, even though non-multiple, those are called interharmonics. So I'll be talking that. So for all these things, to solve those here issues which I was talking here, I said it is the power electronics devices in the grid integrations is one of these. So power electronics provides the necessary voltage and frequency capability between the renewable energy sources output and the utility grid. Optimally control the renewable energy sources for maximum energy yield among the other objectives, provide active and reactive control during the normal operation and the disturbance event. So these power electronics we can control very efficiently. They are very fast controllers, and that basically they utilize, and that's why they are used in the system. Now you see this is a simple here the load. You can say how this is a PV system is there, and now this if any current which is flowing, it is keep on moving at the various nodes here, as I said, and this you can see. So we are having a lot of even the devices that is a custom devices, custom power devices, unified power quality conditioners, the StatCom, dynamic voltage restorator. Many things are basically again used here in the system to again improve these and to minimize to mitigate these harmonics injections. So the harmonics and interharmonics into the systems adversely affect the power quality, and that's one of the concern also, how they are going to be injected and how we can go to estimate first. Because harmonics and the interharmonics, first I should know whether these components are there with our power electronics devices also. So why it is a concern, we all know and we have studied in our various basic courses that it will increase the losses, it will increase the noise, the torsional oscillation of the turbine generator motor load pair set. The torsional oscillations, what happens, there is a generator shaft can be broken if the huge frequency component is entering and the torque is generated NT of the torque which is generated in the turbine generator system. The mal-operation
Sir, your voice is not audible, sir.
It is audible?
Yeah, now it's good. Yeah, okay. Now it's good, sir.
Okay. So now, yeah, sometimes there is some loose connection, I believe. So it is the aging and the failure of the equipments, resonance problem, and you all know the interference with the communication lines, you can say. So you can see this is a signal which is there that has 3 components. One is a fundamental, on the second and third harmonics we have added, and you can see how it is looking. So it is looking at sinusoids, but it is having some jerks are there. So we can basically very well that can be broken in the different sinusoids. Any signal can be broken in the different sinusoids having fundamental and other. It's a multiple of those fundamental can be measure. So these are basically this is the fundamental component first part, and others are known as the harmonics. Various standards are there for how much limit that we can inject in the grid without any disturbance. Lot of standards are there for harmonics measurement and estimations. The power quality measurements, not only harmonics, as I said, harmonics is one component, but apart from there is other things are also, then power quality measurement is also given in IEC 610000430. Also the utility interface of the PV, this if you are interfacing, then how much this, what is your standards and other things are given. The power quality of the grid connected wind turbine is also the PV, and others you can say they are given separately. IEEE also has come with the all interconnection of distributed energy resources with the grid, and harmonics limit and measuring and estimation also 519 is related to the measurement of harmonic. So mostly this IEC, International Electrochemical Convergence Devices as Association, and the IEEE, they are basically having some standards. Normally we follow the IEEE as well as the IC as well. So they are there. So what I can tell you, because most of the device, you know, the first very popular device is a fluke. And you know, you are having the Dranes, you are having Yokohama, you are having Hikoi, all these power quality devices, just you can put some probe and you can say these are the sensors, just cable will pass and then you can very easily you can detect. So these devices are very well applicable and available in the market with a very reasonable and very fast also. And these devices are basically working on the fast Fourier transform, FFT. Or you can say digital Fourier, DFT. So they are basically related to that. Based on that signal, once analog is there, so we can go for the digitization, and based on that we do process it. So these three and many other devices, locally also, these are the standard, many other devices are there. So they work on the FFT. And as you know, the FFT has a certain limitations in terms of measurements. So what we require, the available measuring instruments, the key the points are that should be that the mainly should be used for the visual and easy monitoring of the PQ devices. So whatever the devices was I showed in the previous slide, they are suffering from all these things. For example, mainly as you can say very visually, you can see what is the TSD, what is the individual component, you can see in the web shape also it is possible. So easy monitoring of the PQ parameters you can do. It has a low tolerance of fundamental frequency deviation. For example, your device is set at the 50 Hertz, and during that it's changing, something frequency change. Then if the frequency is more changed, then again this will give the wrong information. So only they are working perfectly all right with 0.03% of deviation. Now you can say very small deviation, it is okay, but if your deviations are very sudden and wide, then they will give you the wrong information. Low tolerance of sampling rate. Deviation. If your sampling rate is deviating, that is also giving a lot of problem here in that deviation. I want to say here, this is a sampling rate, means suppose your 50 Hertz cycle, you are taking one cycle complete data, and by the way, mistake you have taken 1.1 cycle. Yeah, it's a different cycle, more not an integer multiple of the cycle. Because once you are capturing data, you don't know, because again there will be harmonics, zero crossing, etc., and you may miss, and then again it will give you the wrong result. I'll show you. Also, they are not able to measurement of interharmonics. As I say, it is not possible, so low resolution. Means it can only give the harmonic component, not the interharmonic. So for example, to understand the interharmonic, suppose your frequency is 50 Hertz. So the 50, 100, 150 means 50 multiple are harmonics. And any other than in between, any frequency which is not at the 50, 100, 150, then they are basically known as the interharmonic. So they cannot measure. And also the low accuracy between the subgroups and grouping provided the cumulative effect. A lot of things, the grouping and subgrouping also we try to do to basically get it so that we can get the signals together. And another problem is the practical signals may not be stationary. Means, as you know, what is it meaning? We say our frequency is a constant. It is not so. If the frequency is changing during your data, then they will be giving the wrong information. to understand this, later also. Okay. So, so what I need, my ideal estimator or measuring devices, which is basically taking data and giving your output. So what features or ideal features are required? That is one of the concern, and we should talk about this. So in this, the all features of estimation means we have to measure frequency, we have to feature the amplitude, and also we have to measure the phases. So these three are any sinusoid signals, as you know, these three components are there. These components, that's the frequency, the amplitude, and the phase, if we can measure. So these should be giving all the estimations, not one or two. Accuracy means it will be giving the interharmonics component, its magnitude, and as well as its phase as well. So they should give you the accurate for all these measurements, and it should be very instantaneous. Means suppose you are giving data and it is after 2 days or 1 day or maybe 10 hours, it is giving a display the data. Oh, you will be frustrated and you will be bored. So it is also equally important that we should get the data as fast as possible and with the less input. Sometimes suppose you are take the large number of inputs and then you are giving output. So again, this is very boring, and the instrument should be given as instantaneous as possible. Another features required, what we require, it should be robust. Robust means there is, suppose you are measuring with the cables. There is some noise, some interference, some harmonics, some even though some sparking, and some of the even though deletion of the attenuation of the signal. So all these things are there. So in that it should be robust. Even the frequency is also changing all the time. The noise may come due to the measuring devices and wire, etc. So then it should not even though affected by these things. It should be low computational burden, means it should be very fast. Then only you can say it is a computational method. Very easily it can give you the data. And that computational processing in that device should be less. If it is more computational, device will be very bulky, very expensive, so on and so forth. And sometimes it will give a, even though very late result and not instantaneous. Also, it should be very easy and simple to implement. Whatever the device, whatever the mechanism, whatever algo you are writing, it should be the simple and easy to implement. And as you know, this is a very, very important aspect of these things. And another is a system independent and adaptive, because suppose you have a device, it is measuring in this one campus, in NIT campus, you are measuring in the IIT campus and giving the different results. That is not well. We want that this device is independent of the system and anywhere you can put it and get the data. And that basically, so not specific to any model or system. So these instruments should work universally. So these are the ideal features of estimator or measuring devices, which is there. Now the various estimation techniques which I'll be talking, and some of the things I'll be giving and some research inputs to you, that which methods I'm going to show. So the harmonic estimation techniques, you know, can be classified in the two categories. One is non-parametric methods and another is a parametric method. So non-parametric method is one is the frequency domain analysis and another is frequency and time domain, because the signal is time domain, mind it, because our signal is a t, omega t plus phi. So this is a time domain signal, which is we can analyze with the frequency domain, and you know the discrete Fourier transform is one of this. So DFT is normally a FFT, whatever you have done. So this is the frequency domain. People thought, because if you are converting the time domain to frequency domain, sometimes you may not, you are losing the time signal, time is stamping when it has upward. So that the time is also required. Then people thought, what, why not we can go for both time and frequency domain analysis, and in that the various, you can say the Wavelet transform, Wavelet-Packard transform, Hilbert-Huang transform, S transform, Cripps-Jet transform. Many transforms are basically to have the basically both time and frequency domain analysis. People say, oh, it is very cumbersome and maybe giving a lot of bad information and wrong information. Why not we can go for something, some solutions that we can go for this parametric methods. And in that, it may be sinusoidal models or stochastic model. So in a stochastic model, you can say autoregressive models, ARIMA models, Prony methods, singular value decomposition methods are there. But the sinusoidal model, you will find it is basically the Sprity. I'll come later and I'll just discuss what is Sprity. You can have the music and you can have the Kalman filter, you can have the artificial neural networks, all type of the artificial neural network that you can use. So the various methods people are doing, if you are going for very accurate, these methods basically the non-parametric methods will not give you your interharmonics. But once you are coming here, you can get the interharmonics, and that by concern I'll show you. That's why we have worked on the Sprity base, where there's another problem in the Sprity method and the ANN basis, which I'll be showing. So Starting with the various transform, as I said, the first part is the DFT, where the Fourier transform converts the signal into the time domain signal into the frequency domain. As you know, here the signal FT is basically the multiplied by I omega t or j omega t, what you can say, integrating from minus infinity to infinity, 1 upon under root 2 pi. And if you're integrating, you can say this signal becomes a line. So it is a frequency, whatever the frequency of this signal is there, that will be seen here. And that is the basically. So it has a strength, a huge strength, is a very low computational burden, very fast to compute. It is very simple and most of the reliable for the stationary signal. I said the stationary signal means if your frequency, but because in electrical signal, the frequencies keep on changing. It is not in your control. It is controlled by the load and generation imbalances. And other signal for live, etc., you can generate. Suppose you are having a function generator, you can set the frequency. It's a constant frequency. But in actual our electrical grid, the signal is not essentially. But we believe if the band is very tight, very low, then we can assume even that few cycles as a stationary signal. And based on that, normally we are doing. But it is a later stage if the variations are very high, you cannot use even though your FFT. So the major problem with the fast Fourier transform is basically, you can say, their poor resolution makes it difficult to detect the interharmonics. It is cannot give. And even though it is there, even though your information will be wrong, I'll show you. First, it cannot give. And even though its signal is there and you are using DFT, okay, I don't want the interharmonics, I want only harmonics, but still it will not give the harmonics correct information. Another, it requires analysis window exactly integer multiple of the fundamental period. Means whatever the data you are taking. So it is a 50 Hertz cycle. So you have to take it is a 1 cycle, 2 cycle, 3 cycle, 4 cycle. It is not you can take 1.5, 1.1. If you are taking and analyzing, it will give the wrong result. So making exact is also one of the very tedious tasks and to do it. Another is the frequency deviation. If the frequency is changed, then what happens? You will find there is a leakage and picket fence effect. Normally we call that is happening. I'm not able to detect the local transient. If the transient is there, gone. So at the time information is completely lost. So that is basically the problem with the Fourier transform. And you see what are these things just also with this diagram. You see this is a square wave I have taken, and this square wave, and what we have done here, I am putting a one interharmonic frequency, you can say here at this point. So it is a fundamental here 50 Hertz. It is a third, fifth, seventh, ninth is was there, and extra one was added here. You can just multiply. You can see it is a 7 into 50, 350, just 25 less. So one here, just I have added. This is a interharmonic. So I want this spectral, and so that I can know what are the harmonics and what is the interharmonics, what is the magnitude of this. But if you are putting this into FFT, you will get this one. You see. You cannot see where is interharmonics, where is other harmonics component are also coming. Even though you'll find that the DC component is coming, even the zero is also coming. So a lot of this component, after doing this, you can get in this form. So that is giving a wrong information. You are unable to get the magnitude properly. You are unable to get what are the other components are there. There are many other components are also coming into the picture, and that is basically not desirable. Now, suppose you are not having interharmonics. Then you will get very exactly without this, you can get with the FFT without any problem. But if you have taken the data of 1.1 cycle, which I said, and it is no interharmonics, you will get this. Now you can say it is all the components are there. A huge amount of DC also is coming. Fundamental is there. So that you cannot guess what are the components, and this is giving a wrong information. If your frequency is changed, as I said, the frequency. No doubt here the frequency I have taken the 50.5 Hertz. That is a very high value because we never allow the more than 50.1 or 2, although even earlier our grid was operating on that. So you will see what we are getting. So now in totality, I want to say that your fast Fourier transform will not give the data if you are having the interharmonics, if you are having your not matching with the close cycles, the multiple of cycles, and also if you are having the frequency deviations, so that you are getting the wrong result. If these are not there, then you can. So if your frequency is 1 cycle, no problem. If your interharmonics is not there, is no problem. If your frequency is fixed, no problem. But if they are there, then. So we don't know in the signal whether interharmonics are there or not. Others we can try to match. Other we can try to match and we can go up to very accurately. But in signal, we don't know whether they are having interharmony. If the signal hit was there and I'm getting this data, what I can conclude, which is very, very difficult. So that's why we have to go for some other methods if the interharmonics, because the power electronics devices, I'll show you, they are having these harmonics as well, interharmonics now. Another transform which is used, basically it is nothing but your, this is your wavelet transform. And wavelet transform, you can say, what is this? Normally it is the breaking of the signal. It's something high pass and the low pass filter. If you are having the frequency in this range, you can have the break 1. So you can say the 500 to 1000. Then here the 0 to 500. Again, I'm breaking 2 part. So it is basically the signal is broken in the different low frequency and the high frequency component. So that you can see. So here getting the exact problem is a difficulty. You cannot get the exact component, but you can get the range of that. But you still also find maybe your problem is somewhere in the larger component and your harmonics are in this range. So then what will happen? For that, what people decided, why not we can also break the high pass filter components as well, and then we can go for the very uniform. So how many labels you are going to know your frequency range, it is also a tedious process, and that's why the wavelet transforms are not very good for basically to identify this exact. But if we are going, normally this signal processing people use these very well because they know this, what is their wire signal frequency. Beyond that, there is a noise. And what in our case, what we know, those noise we want to detect here in our case. So it is all the things are different than what the signal processing people do and what we do. Our frequency range is 50 hertz, that is operation. Remainings are the noise and unwanted signal. For them, even though those are the wanted signal and these lower frequencies are unwanted and vice versa. So that's basically wavelet part. Another, so if you see compare, so a strength are provide the frequency and time information simultaneously. The multi-resolution capabilities are there, more suitable for the transients detections. It can get because we can filter out the harmonics components if they are there, so the high frequency can be taken. And it is a convenient for the IEC standard regime. It was very well used there. But major problem is the computational burden. It provides the harmonics in terms of frequency bands, not exact value. Additional tools are needed for interpretation of the transform parameters. So what are the coming? So we have to go for the detailed and the approximate analysis normally we do. Another is your proning method, which normally very widely people are using. Here what they do, this is basically the proning method is based on the representation of a signal as a linear combination of exponential function. As you know, the sine and cosine can be broken into the exponential function with the imaginary part. And you can say J is coming here. So it has some decaying components alpha and also the magnitude here. So I can basically the action signal can be broken in the different frequency component in the terms of exponents, and that's basically it is a representation. So a lot of variety of the proning methods people have used to determine the frequency, amplitude, decay component, and also this theta. So these things are basically done with the action signal. Only the concern here, because if you're, as you're increasing and going for a very large one, I can tell you here this M component, how many components you are going to analyze, that creates huge problem. So, and if you are more, then time computational is very, very high. So in all these things, what you can do, you can say we create the Wander mode matrix, you can say the V here, and based on that we analyze, and that's basically the very cumbersome process. So it is again, the lot of people have worked with the modified prony, many type versions are there people are using. So the able to identify damped components and the damping factor as well. Other methods are not giving the damping component. And high resolution without leakage it will be giving. Only the problem computational burden, sensitive to noise, and also the model order M, which I was talking, is difficult. And inaccurate model order will give the very wrong information. So that's why the selection of M, if you are taking M very large value, that's very time consuming. If taking M very short, fast analysis, but the wrong information can be got. Kalman filter, as you know, the estimation theory, I'm not going, even using the Kalman filter also, we can get the best fit, we can minimize the noise, and based on that we can get, and that's a Kalman filter also people have a use, but not especially for the harmonics or interharmonic component. So the Kalman filters basically the main strengths are the information is processed immediately, unlike the batch processing methods. Online tracking of the variations is possible. It is highly robust against measurement noise and the model order, but the only problem is the convergence Another is suffer from the filter divergence, and the optimal filter tuning parameters are again the error covariance matrix is a difficult, and it results in the poor one. Another is people are saying why not going for the AI application. AI application, as you know, this is nothing but anything can be mapped here. It is a black box, and here my input and output is whatever you want. I want my amplitude, I want my theta, I want my frequency. So I can have some sort of mechanism with having the neural network, artificial neural network, and we can tune for the unknown parameters. For known parameters, we can get the tuning and everything where error can be minimized. And for unknown, if you are giving the signal instantaneously, you can get those components. So it is very fast also. So what they do is the mapping here. You can say this signal is having the various signals we can have, and that's having various layers, hidden layer, input layer. As you know, I'm not going to explain. Having the various weights and other things, I can get my outputs, and that is basically main purpose of artificial neural network. The strength here, the trained neural network needs only just a half a cycle data to provide the fast estimate. Here, only half of the cycle is sufficient, not even the complete cycle. Others we require many cycles, not only one cycle, many cycles. So then again, it's a computation is going to be very simple. It's adaptive. You can change it always. If the signal is changing, you can change it accordingly. So, and it is a very robust against noise, and if trained properly, otherwise it is having a lot of problem. Is only a predefined frequency component can be obtained, can be trapped in the local minima, multi-layered complex structure, difficult to implement, new data patterns and transient results in more error, difficult to obtain efficient and the suitable training. Having these problems, we also tried with the certain and also some of the examples where we use even the artificial neural network, and we found it was giving you the good results as well. Another is our splitting method. This is the estimation of the signal parameter via rotational invariance techniques. So it is a parametric method, which I said in the beginning, that represents the distorted signal as a sum of sinusoids. Prony is the sum of the exponent signals. So it's the sinusoids, and then use the sequence of observation to obtain the parameters of the model by dividing them into the signal. And what we do, we just go for the different subspace. We are creating the different inputs level of the signals at various level. You can say this K is basically what is the value of M that we are going to solve. So here we are taking up to M. M is a model order, and then I can create these signals here. You can say in this matrix. So once you are having this matrix, so you can go for the eigenvalue decomposition. Wait. And then after this eigenvalue decomposition, we can go for the signal and noise space, because they are having the different frequency spectrums. You can very easily, we can separate. And once you can separate, so using the shift invariance property, you can get the least square minimization. You can measure the frequency, and then from frequency, you can measure your amplitude and the phase. So that's basically giving very accurate results and very good. Only this concern is what should be the order of this matrix, means what should be value of M, because we don't know in the signal how much M. So people keep on talking and doing a lot of research to find the optimal M, and this is called model order. So if the M is optimal, we can get the very accurate result, and also some of the examples here. So the strength is a high resolution, therefore precise frequency estimation, early robust against noise, accurate amplitude and phase estimation, no need of training data, the prior system knowledge for the modeling, but it requires the computational requirement, low accuracy for non-instruction signal here also. So these are the concerns in the splitting method. Also some example, and then which we did and we published in the IEEE Transaction on Sustainable Energy. So even you can say the artificial neural network which was talking, we slightly changed this neural network with the adaptive wavelet neural network. So the adaptive wavelet neural network was used for the harmonic estimation in the wind and PV system. So you can say this is your signal, and only I can take half of the cycle here. For the input, we have to, this is your signal, where I'm taking the few data and this half a cycle, and that it will be given to our model. So this is our neural network where we give only this is a wavelet, adaptive wavelet neural network, because we are using instead here sigmoid function or tanh functions normally used. Sometimes use the Gaussian function. So this is called the radial basis neural network. Here, if you use the wavelets or wavelet transforms signals, this is a mother wavelets. So then it will go at a wavelet neural network. So in this, what I do, this is the signal which I am putting. You can see this is a half a cycle. This is the signal is broken with a different input. After training, I can get my output, and these outputs are amplitude, phase, and other various frequency components we can get. So we use for this with these parameters, and with having a half cycle 32 inputs, having only one hidden, and we use 8 wavelengths. Mexican hacked wavelengths are used, and number of output I've just found 4, and you can see it's not very important. So they are basically applied for the PV system first. So this is a solar panel, and you can say having the boost converter and this line commuted inverter, and then having the some controller and MPPT controller there, it is connected to the grid, and we measured here in the data. So you can see this output of this this PV system will be coming like this. So it is a sinusoid. It is a sinusoid, you can say, and we try to find with the help of actual signal. This is actual. This we basically get this amplitude with the adaptive wavelet neural network and FFT also. You will find this is it is giving better result, even though you can find some of the small amount of FFT is coming, because it seems there are some interharmonics and very small components are there. So that basically it is creating some of the problem, but adaptive wavelet neural network is giving good results. And you can also, there's error. Adaptive, this blue is the error basically, and this is in various harmonics order. They are very small value. You can say 10 minus 3, 10 minus 0.1% here, 10. So these are the percentage, 10% error you can say find here, but here you can say it is less than 0.1%. So blue signal you can see. So this is it is giving the better result compared to this. We also use the same AWNN, and you can see this is here the full grid converter is a permanent magnets. Synchronous generators are used, and then we are having the rectifier and inverter and connected to the grid here that is used. And in this signal, you can say you can measure. You will find this signal is coming at the output. And again, we tried with this, and we found that our adaptive wavelet neural networks is giving. But you can see very small, minute. The magnitude is so small, even though a small change will be giving some here and there. But magnitude of the first, second, and third, which is more, and that is that basically this signal is this analysis is giving better result. Here you can say it is more, but this in percentage wide, that is almost negligible. Normally we ignore also 7th harmonic. So that basically is giving the beauty of this. Another study what we did with the splitting methods, and here we use some synthetic signal. We use some mathematical signals, and also we use some practical signals. So you can say we use the this simulated signal. This is the mathematical what we did. We had my amplitude, the frequency, and phi, and we have added here. You can say the true value I have added with this, so I can generate a signal. So it is having the interharmonics 1, interharmonics 2, and then is my actual value. Putting all this here, I can get this I need from all the analysis. So it is IEC subgroup analysis, Prony method, sliding splitting, and exact model. We developed one techniques so that we can minimize the timing, and that's basically that was one of the transaction paper we published here. Using all these methods, you can say this time requirement is very less compared to all the methods. Only the IEC group is very fast, but you can find here this value is, you can say it's very high, 1.1% reconstruction error. Here is a 0.0117 it is coming. So that's the error and time. If you're compromising, it was found this is a splitting method is good, even the for the simulated. Here, no doubt, we are knowing the component. We are knowing the component. If you don't know the component, then I will also show how it does. So what we did, we basically here use the laboratory setup for acquiring the actual signal. So we use all type of power electronics devices. You can see we are having the dimmer, we are having the mobile, we are having laptop, probe, LED lamp, CFL, CRO, desktop, all we connected. And basically now you can see once you are connecting, then how you can get the actual signal. What happens in our laboratory, in IIT campus, even in our campus, if you measure, you will find that the frequency, even though your signal is so bad, it is not a sinusoid sometimes. So what normally for the lab purposes we do, we take the signal and then finally we rectify and then we invert it so that we can get the perfect sinusoids, and then I can use for all these loads, etc. So using this data analysis here, also we use here the DAC, and finally you can see use for our purposes. So our supply voltage, once we measure for this load setup, you can say this is a sinusoid, but it's not perfect sinusoid. So then we analyze using the SPT methods of harmonic estimation, and you can say the harmonic estimation component we find by the SPT, we are getting the fundamental is the highest large value, and other value components are there, but very, very small, very small. So what we do with the knowing this component, we make another signal, and then we compare with these two. This is the actual one. This is the reconstructed, means after the analysis I found these components with my method is giving. You know, to check the validity of any method here, what normally we do, let's say your original signal is there, and once you analyze, you apply your algos, you apply your methods, and then you find certain component. With these components, you can generate signal again. And once you are generating, this is called the reconstructed signal after analysis. And once you are subtracting these two, and what error you are getting, if it is a very small, then I can say my model is correct, my method is correct. And that you can say the error is very, very small. You can say it is a very small value which is coming in there. This error is basically in the values. Another, even though we found that you can say that the various reconstruction error with the SPT method, sliding, Prony, IC group. So the computational time also you can say this method is slightly good. And also the mean and maximum, because every time you have different window we took, you know, because right now you are taking certainly some deviation is there, then the different value is there. So what we did, we go for all the changes in terms of its loading and other things, and finally the maximum mean value and the standard deviation we calculated. And finally we found that this is a reconstruction, you can say standard deviation is very, very small. Only it is poor than this, but you can say the error and this error you can find. So that's basically the beauty of the SPT method. Another the current signal which we miscellaneous, whatever the nonlinear loads we used, then we find that this is the signal we are getting. You can see how it is. So this is a current signal, and then what we analyzed, and after the analyze, I'll show you the table, and based on that those frequency component, we reconstructed signal again, and you can see they are very close, and we subtract from these two signal, and this is the residual error, and if the residual error is small, you can say 0.5%. Is very, very small, and then I can say my method is correct. So for that signal, you can see here we analyze with all the methods, Prony method, sliding SPT, and modular. So this is our proposed basically method which we find certain algo we develop so that we can get and the time can be minimized. So you can find this is giving a time is also comparable. No doubt, as again here you can see this time is less, but the error is high. Here error is very less. So there is some problem here. I think error is here very high. It is not 0.65. So it all depends how much component you are having in your frequency component. You can say this is all integer components you are having. So if you are having the interharmonics, that is creating a lot of other problems. Basically, I'll stop somewhere because if you have some questions, etc., that is also very important. So due to increased penetration of renewable energy sources and usage of power electronics devices, the power quality is going to be a major concern in the near future. Right now, our percentage is less, and we are interconnecting at the lower voltage. So the harmonic which is entering in the major grid, because from the load it is injecting, and finally we are having the resistances, we are having the lot of even the earthings and other components those are short circuited. They are basically going to the ground, and that you can say its magnitude, its impact is minimized. But if you are going for the big, large wind farms and larger one, then its impact is going to be more and more. Apart from harmonics, the interharmonics are also to be estimated accurately, because if you are going to have a more and more power electronics devices, because one in harmonics which is entering in the power electronics device may generate another harmonics and another interharmonic. So it is a cumulative effect. It is a cumulative. As you all know, these power electronics are very good, and they basically for the power quality issues. They solve the power quality issues. But if there is the power quality they generate, and that is adversely affect to those devices. So it is basically the cumulative effect is going to happen. Better estimation and the measuring tools are required. Already I told you for the efficient mitigation of power quality problem. So we have to basically, tools are the measuring tools. No doubt we are at this moment of whatever the devices we are having, they are giving the very accurate. But if you require more and more analysis with the interharmonic, that's you have to think for some other algos. It can be concluded that every method has some pros and cons. As you see, no method is perfect. No method is perfect. So depending upon the application requirement, that is accuracy, speed, signal noise levels, etc., the suitable method should be selected. So it is, you can say, all the methods are having pros and cons. No method is perfect. If it is perfect, so people should have gone. So you have to decide what is your requirement. And based on the application requirement, that you have to choose the device or method for finding all these things. So the future scope and challenges, the intermittent nature of renewable energy sources produce time-varying harmonics, and which is difficult to estimate and track. Even the standard IEC and IEEE consider signal to be stationary, which is invalid in our upcoming scenario, which is going to happen in the future. The estimation accuracy is also suffered in the presence of other PQ problems, such as voltage swell, and transient. Suppose there is a transients coming, sag is coming. If you are using device, this algo, what will happen with that impact? Whether they are going to erroneously give you wrong information, your analysis is going to be invalid. So all the things are having the multiple of power quality problems. In those conditions also, your estimation accuracy should be maintained with a certain percentage. And that is another challenge, because if you're having many problems, that certainly even whatever analysis I showed, you add something more, you will find something more. And that is one of the concerns. So the consideration of the CT and PT effect and the actual and the measuring signal is still an open field for the high and medium voltage application. So the CT PT, because you cannot go for the 11 kV, you cannot go for 100 of amperes current measurement. So what we do, we go for the taking with the probe, we are going for the various sensors. We take sometimes the CT and PT voltage, etc. So that is also having the very good quality. Otherwise, they will be also giving a lot of other wrong information, which is not a good, which is not valid. So many problems are there, and many things are there, which is basically having huge potential to do the research in these directions, especially in the power quality related issues in terms of estimation. So with this, basically I'll end here, and I love if you have any questions.